with an eye fit to the guy. But that's in the science section.
Oh my god, so funny. Carter, watch out for that leaf!
And while we're down here, let's talk about chemiosmotic phosphorylation.
Bill Nye the Science Guy. Bill Nye the Science Guy.
Let's begin with our basic equations.
Photosynthesis, which is 6 CO2 plus 6 H2O yielding C6H12O6 plus 6 O2. And then cellular respiration is 6 O2 plus C6H12O6 yielding 6 CO2 plus 6 H2O and ATP.
Well put, Lauren.
But which cells can perform either of these processes?
Well, Lauren, all organisms do some form of cellular respiration, but only autotrophs perform photosynthesis.
Oh, right. And plants perform photosynthesis in order to harness energy from the sunlight and turn it into chemical energy. Most autotrophs need this process to function and survive. On the other hand, respiration is the process of converting chemical energy into a more usable form of energy. All cells can go through some version of this process, whether it is anaerobic or aerobic.
Right.
But wait!
Yes, Carter?
Where do these occur in the cell?
I don't know.
Good thing I do. Photosynthesis is broken down into two parts, light reactions and dark reactions. Both of these reactions take place in the chloroplast, as depicted here. Light reactions occur here, in these in the membranes of these little pancake guys called thylakoids. Dark reactions, also known as the Calvin cycle, occur right over here in the stroma. Cellular respiration gets a bit more complicated.
Wow, this guy really knows his stuff.
For respiration, we have 3 parts. The first is glycolysis, which occurs right here in the handy-dandy little cytosol of the cytoplasm. Second step is the Krebs cycle, aka the citric acid cycle. And the third step, Stevie Nicks' favorite, is the electron transport chain. The citric acid cycle and the ETC go down here, and in the mitochondria. Say it with me, kids, all together. In the powerhouse of the cell.
Wow, Carter's really smarter than I thought.
Wait. What about oxidative phosphorylation?
Wait, I think I know, Julian. I believe oxidative phosphorylation is the last step of respiration and happens in the inner membrane of the mitochondria, the powerhouse of the cell.
Oh.
Oxidative phosphorylation occurs in the ETC in respiration.
Your clothes look different.
But how does that happen?
Well, basically, NADH and FADH2 take electrons from the intermembrane and create a gradient of H pluses, which causes the concentration of those H pluses to increase. This gradient of H pluses creates ATP by flowing back into the ATP synthase. Any more questions, Carter?
Wait, I have one. Isn't there a gradient for light reactions and photosynthesis as well?
There sure is. For light reactions in photosynthesis, the water is broken apart and the concentration of H pluses become higher in the lumen and lower in the stroma. Because of this contrast, the proton gradient is made. In addition, there is an electron transport in the thylakoid membrane that pulls more H pluses into the lumen and adds to the gradient.
Oh, I get it. So basically, both oxidative phosphorylation and photophosphorylation happen on or across a membrane. Intermembrane for oxidative phosphorylation and thylakoid membrane for light reactions. And both increase concentrations of H pluses on one side of a membrane. It's called oxidative phosphorylation and photophosphorylation because both processes involve making ATP by adding P to ADP. Oxidative phosphorylation is for cellular respiration, while photophosphorylation is for photosynthesis.
Yeah, exactly. Both generate energy too.
Wait, before that, can you define chemiosmotic phosphorylation?
Breaking down the two words, chemiosmosis is the movement of H plus ions from high to low, while phosphorylation is the addition of a phosphate to ADP to make ATP, as shown over there. Together, chemiosmotic phosphorylation is the movement of hydrogen ions across a membrane in either photosynthesis or respiration, which yields ATP. Basically, these ions move down their concentration gradient across a membrane. The production of ATP all happens in the matrix of the mitochondria and the thylakoid space of chloroplasts. But wait, Carter, there's more! In the light reaction, there's an electron donor and a chemical reaction that actually contribute to the gradient. The electron donor of a light reaction is water, or H2O. The H2O is split, and the H plus ions are separated, while waste O2 is formed as a waste product in photosystem 2. The buildup of H plus leads to a change in the concentration of ions in the thylakoid space.
ATP is formed from this movement down the gradient. In photosystem 1, however, H plus ions bond with NADP plus to form NADPH. These two products stimulate the rest of photosynthesis.
And then in oxidative phosphorylation, the electron acceptor is oxygen. The electrons go through the electron transport, which moves the electrons and creates the gradient. They then go back through the ATP synthase, where ATP is created through phosphorylation. The leftover hydrogens now bond with the pre-existing oxygen and create, wait for it, water.
Anything else?
One last thing. The way in which ATP synthase converts the mechanical energy stored in the chemiosmotic gradient into ATP is by letting H plus ions flow through, releasing the energy built up by the concentration gradient. It is then used to bond phosphate to ADP, which creates the ATP. ATP synthase is an enzyme for chemiosmotic phosphorylation to help make ATP.
Wow, what a clear, informative lesson.